Hello! In the last video we saw visually that quantum wave packets corresponding to free particles blur out in space over time. This phenomenon is known as wave packet spreading. Today we will define spreading mechanisms and value of spreading velocity or spreading rate of wave packets. As we know, a classical particle of mass m flying with velocity v can be represented by a wave packet consisting of many de Broglie waves with close equidistant wave numbers allocated symmetrically around some average value k. The group velocity of the packet u group, that is the speed of movement of its center, is equal to the classical velocity of the particle and is equal to h bar k over m. Thus, in the studied case, the group velocity is determined by the average value k over all value numbers. If we divide the packet into two equal parts along k, we will get two subpackets whose movement velocities will be slightly different. For a fast subpacket located on the k-axis to the right, we will have a group velocity u fast is h bar over m multiplied by average k value, that is k plus a quarter of delta q. Here delta q is the overall range of wave numbers in the entire packet. Quite similarly, for slow subpacket we have u slow is h bar over m multiplied by k minus a quarter of delta q. When dividing a packet into two parts with a total odd number of waves, we will add the same central de Broglie wave to each of the subpackets. This is not entirely correct, but will not affect the overall correctness of our conclusions. Due to the difference in their velocities, the fast and slow subpackets will gradually spread away of each other. It is quite reasonable to assume that the speed of their relative movement will be equal to the speed of spreading, or in other words, the spreading rate of the main packet. Thus, the spreading rate W is equal to u fast minus u slow, which is equal to h bar over 2m times delta q. However, our definition of the spreading rate is not strict. Each of our two secondary subpackets can further fall into tertiary subpackets and so on. But it turns out that it is not possible to give a more precise definition that works in the general case by diving into a more in-depth analysis of the spreading mechanisms. Therefore, we will leave the simplest formulas that we just derived, but we will treat them not as exact relationships but as rough estimates. This is the generally accepted approach for this problem. In order to emphasize the evaluative nature of our formulas, it is the usual practice to use the tilde symbol instead of the equality sign in these expressions. This means that W is not exactly equal, but is of the same order of magnitude as h bar over 2m times delta q. Frankly speaking, we have received the main formula we need and can continue further discussion of how this formula works. But in textbooks you can find a more general formula with second derivatives of frequency with respect to wave number. Now I will show for reference purposes how to derive this general formula without prior knowledge of differential calculus. I will mark this material with the warning caption advanced. Our review will not be too complicated, but a bit boring. Therefore, you can just listen to this topic on your first viewing without trying to understand all the details. You can return to these explanations later, if necessary. Suppose we have a packet consisting of some of elementary traveling waves with equidistant wave numbers allocated around the average wave number k. Applied elementary waves are not necessarily de Broglie waves. Then suppose that we have some relation between frequencies omega and wave numbers k of these elementary waves, which is not necessarily quadratic, as in case of de Broglie waves. Following the method we just used, we will divide our packet into two subpackets according to their wave numbers. Let's assume that similarly to the previous case of de Broglie waves, the subpacket located to the right of the average value of k moves faster. To estimate its speed, we will take only two waves, namely the central elementary wave with wave number equal to the average value k and the rightmost wave with maximum wave number equal to k plus half of delta q. As you can see from the presented figure, we will denote the frequency of the central wave as omega of k, and the frequency of the rightmost wave as omega of k plus the half of delta q. According to the general rule defined in our previous stories, the group velocity of such a subpacket composed only of two waves is equal to the difference in frequencies divided by difference in wave numbers, that is omega of k plus the half of delta q minus omega of k, all divided by the half of delta q. Of course, in the case of the Broglie pocket, this formula can be reduced to the previously obtained relationship U fast is h over m times average wave number, k plus a quarter of delta q, identified for the fast subpacket constructed of two waves. You can check this yourself. Quite similarly, we identified the group velocity of the slow subpacket as omega of k minus omega of k minus the half of delta q divided by the half of delta q. Spreading rate is then estimated as the difference of identified group velocities of two subpackets, which is equal to omega of k plus the half of delta q minus 2 omega of k plus omega of k minus the half of delta q all over the half of delta q. If we now multiply the numerator and denominator by 1/2 of delta q, then we can rewrite the spreading rate as the product of a variable coefficient a and half of delta q. According to our definition, coefficient a depends on both k and delta q in a rather complex way. However, it's possible to construct a simpler estimate for a, in which a will depend only on k. In order to do this, we will replace the real function omega of k with an approximate quadratic curve. Let's consider the central point of the pocket with wave number k and the angular frequency omega k, and two more points to the left and right of the center, both located at an extremely small distance delta k and having frequencies omega of k minus delta k and omega of k plus delta k correspondingly. The angular frequency is proportional to the square of the wave number for the Broglie waves. In contrast to this, we are now considering the general case when this dependency is not quadratic, but through any 3 points located in the plane, we can draw a quadratic curve, also called a parabola. Let's write down these quadratic dependencies for 3 points shown in the figure and construct a parabola based on these relations. As an argument, we will use the increment delta k of the wave number relative to the central point. For the central point, the argument increment is 0 and the frequency is equal just omega k. For the leftmost point, we have omega of k minus delta k is equal to omega k plus b times minus delta k plus c times minus delta k squared. For the rightmost point, we have omega of k plus delta k is equal to omega k plus b times delta k plus c times delta k squared. If we add these two equations together and do some transformations, then we can get an expression for the doubled coefficient c. In general case, this formula gives different results for different delta k's. However, if delta k tends to 0, then the result will not depend on delta k and will always be the same. We will denote this value as 2ce, where the superscript letter e is used as an abbreviation of the word estimated. Now we can calculate the value of 2ce for the special case of the Broglie waves. As we see, it is equal to the Planck's constant h bar divided by the mass m of our particle. Note that this value doesn't depend neither on k nor on delta k. It should also be pointed out that the limiting formula we obtained is none other than the so-called second derivative of the frequency with respect to the wave number. Indeed, by definition, the first derivative is equal to the limit of the ratio of the difference between the values of a function at 2 points to the difference in positions of these points, provided that the difference in positions becomes infinitely small. The second derivative is the derivative of the first derivative. It is determined based on the forward difference and the backward difference, which is fully consistent with our formulas. Hence, it appears that the coefficient 2ce is exactly equal to the second derivative of the frequency with respect to the wave number. In exactly the same way, we can obtain the limiting expression b for the coefficient b if we subtract above mentioned quadratic equations from each other and then make not too complex transformations. You can check it yourself. Note that for estimation of the first derivative, we use here the concept of central difference. Now, knowing the coefficients b and c, we can construct an estimated quadratic curve which is shown in the figure as a dotted line and which approximately describes the real function omega of k. Any point on this dotted line is described by a quadratic relation of the same form as the previously studied quadratic equations. But now the coefficients be and ce are the same for all points on this curve. Thus, using the formulas obtained earlier, we can express 2ce in terms of the values of the approximate function omega e of k in 3 points on this curve with arguments k minus delta q, k, and k plus delta q. This expression for 2c coincides in substance and in form with the expression for coefficient a in the formula for the speed w of packet spreading. Replacing a with 2ce, we can get the final expression that the spreading rate w is equal in order of magnitude to 1/2 of delta squared omega by delta k squared times delta q. For the packet of de Broglie waves, we have w is about h bar over 2m multiplied by delta q. Here we must especially emphasize that for a packet of de Broglie waves we have already obtained the same result at the very beginning of the story in a much simpler way without using any derivatives at all. The reason why we also explained the more complex method based on the use of derivatives, or more generally on the expansion in the so-called Taylor series, is that this method is traditionally used in textbooks since it works not only in quantum mechanics but also in other areas of physics. Now we are done with advanced materials and can continue moving forward with more simple basic concepts. In order to check the validity of our formulas, we will monitor the change in the width of the packet over time. We will denote this time-varying packet width as S. It is reasonable to assume that the right and left wings of the packet remain approximately unchanged, and only the middle part of the packet broadens apart from 0 to Wt. If the initial width is delta x, then after time t, the width s will be about delta x plus Wt. For the Broglie waves, s about delta x plus h bar delta q over 2m multiplied by time t. Now we will see how this works for a packet of de Broglie waves made up of 21 cosines. We will assume that the half of the initial packet width, that is delta x over 2, is equal to the distance between the origin and the nearest point to the right at which the packet envelope turns to 0. At this point, the argument of the upper sign in the envelope becomes equal to pi. If we assume that 2n plus 1 over 2 is approximately equal to n because n is large, and also take into account that n delta k is equal to half delta q, then we can get that delta x is equal to 4 pi over delta q. From here we can get that S is about 4 pi over delta q plus h bar over 2m times delta q times time t. In atomic units applicable in our case, we have S is about 20 pi plus 0.1 t. If we visually compare estimated width with the observed evolution of the packet, then we will see good agreement. In the presented animation, we use direct computer calculations of the sum of 21 cosines at various points along the x-coordinate at different moments in time. But monitoring moving packets is not very convenient, therefore it is common practice to consider packets with motionless central point corresponding to particles at rest. We will call them standing packets. They have zero group velocity. To assemble such a packet, we set k to 0, but keep all delta k's as before. As we might expect, observable width of the standing packet matches also well with derived relations. Note that in the case of a standing packet, as in this example, we no longer see the typical zigzag carrier wave usual for a moving packet, as we observed in the previous example. The carrier wave for a packet symmetrical in wave numbers is represented by a cosine function, with wave number and angular frequency corresponding to the center of the packet. For the standing packet, both the central wave number and angular frequency are equal to 0, and therefore the carrier cosine degenerates and turns into the constant equal to unity. For this reason, the carrier wave disappears, and only the envelope wave remains, exactly as we see in the last example. We have already discussed in previous stories that the full-scope time-dependent quantum wave functions are always complex functions consisting of real and imaginary parts. Spatial changes in the real part induce temporal changes in the imaginary part and vice versa. This is a common mechanism that generates oscillations in time and space. Our packet of 21 cosines represents only the real part of the wave function. Imaginary part is given by the sum of sines with same arguments. To observe the spreading of such a packet, it is more convenient to work not with the function itself, and not with its real and imaginary parts separately, but with the square of its absolute value. As we said earlier, the square of the absolute value of the wave function at a certain point x multiplied by the value of some space interval delta x, including point x, determines the probability of detecting the particle within the interval delta x. It is seen from the presented animation of the squared modulus of the fully fledged time-dependent wave function for the wave packet composed of 21 de Broglie waves that our estimations describe this process adequately. In the next story, we will look at the important case of Gaussian packets and the main features of their spreading. Please do not hesitate to leave your comments under this video if you found the story helpful or if you noticed any mistakes. Your comments are very important to improve the quality of these materials. Thank you for attention.